This is Earth, the planet we all know and love. As most of you probably know, Earth is unique and that's the only planet known to have life on it. But why is that? While biologists will tell you about the first self-replicating RNA and evolution, astronomers will tell you it's because Earth is found in a specific part of our solar system called the habitable zone, or colloquially called the Goldilocks zone. Because carbon-based life, such as the life we see on Earth, requires liquid water to exist, the habitable zone is most often defined as the range of orbits in which a planet can sustain liquid water, or where its average temperature is between 0 degrees Celsius and 100 degrees Celsius. But how does one go about calculating the range of orbits that may make a world habitable? The first step is to realize that heat is a form of energy, and so a planet will maintain a constant average temperature when the energy absorbed by the planet is equal to the energy radiated by that planet.
The equation for the rate of energy radiated is shown here as E sub r, where r is the radius of the planet, sigma is the Stefan-Boltzmann constant, and T is the temperature of the planet. It's interesting to note that this highlighted portion of the equation is the equation for the surface area of a sphere.
Because planets radiate energy through their surface, it would make sense for the energy radiated to be directly proportional to the surface area of the planet. In addition, the Stefan-Boltzmann equation states that the heat power emitted from a surface is equal to the fourth power of its temperature, which is why the temperature is to the fourth power in the equation.
The equation for the rate of energy absorbed by the planet is shown here as E sub a, where r is the radius of the planet, L is the luminosity of its star, A is the planet's albedo, and D is the planet's distance from its star. If we look at this highlighted portion, this is the equation used to find the rate of energy through a single point. If the denominator looks familiar here, that's because this is once again the equation for the surface area of a sphere.
This is because luminosity is the total energy output per unit of time, but as it releases this energy, it spreads out in a sphere around the star. As it spreads out, the total energy stays the same, but the density decreases proportionally to the surface area of this energy sphere, which is why we see this equation here. Since the planet is a sphere though, it intersects more energy than a single point would. It actually intersects energy equal to its cross-section, which is a circle, hence the pi r squared. This is finally multiplied by 1 minus a, because if a is the percentage of energy that's reflected by the planet, then 1 minus a is the percentage of energy that's actually absorbed by the planet. Setting these equations equal to one another gives this, and solving for d, or distance from star, and simplifying gives this. And here we have it, a relatively simple equation for solving for the habitable zones of a star. Using these equations, astronomers can scour the universe for planets with the potential for liquid water in an effort to answer the question, where are the other habitable planets, and are we alone in this universe?